several possible breakdown effects um, that might occur in the device. So one of those is the drain to substrate PN junction. It might break if the applied drain voltage is too high and avalanche multiplication occurs. The thing is, if you have a device like this, so let's see if we have a, yeah. Now this, for example, this drain terminal is kept reverse by, this is a PMOS device, PMOS MOSFET. And if you go on increasing VST over here, well, this depletion region is going to increase. Okay, this region is going to grow, and at a certain voltage, when VST is much larger. Okay, you see this is like a PN diode over here, a reverse bias PN diode. Okay, this is P, and then you have a negative battery terminal. So this is a reverse bias PN terminal, and then again it has a N-type substrate. So there is a reverse biasing with the substrate of the body as well. So this depletion region is growing with the VST. All right. So a point occurs when the diode breakdown occurs. Okay, and when the junction breaks down due to the large electric field being supplied by VST, and the avalanche breakdown occurs. Okay, so there's a multiplication of current, and if the current is high enough, well, the device might burn down. Okay, so this is one of the possibilities of the breakdown in MOSFET. So so as the size of the device becomes smaller, okay, for smaller channel devices, another breakdown mechanism is called punch through, which might become significant for small channel or small geometrical sizes of MOSFETs. So a punch through occurs when the drain voltage is large enough for the depletion region around the drain to extend completely through the channel and to the source terminal. This effect also causes the drain current to increase rapidly with only a small increase in the drain voltage. So what happens in punch through is that as you are going to increase this VSD, a point might occur that, well, this is going to interfere with the channel. Okay, and the channel geometry will be something like, it will be tapered off. Okay, we have discussed this before. So you're pinching off the channel, but as you go on increasing this VSD, this depletion width is going to it's going to throughout cover the channel of length L. If the device is small, you won't be needing much higher VSDs for longer length devices or large MOSFETs having length dimensions greater than equal to 2 micrometers. Okay, for large channels you don't have this problem, but for smaller devices like zero point 0.2 micrometer or less, those small channel effects, they come into the picture. Okay, and one has to take that into the consideration. So even a small increase in VSD is going to increase the ID significantly. Okay, so the ID is going to increase significantly because you see the drain is just like it's short circuited with the source. So you don't need to even create an inversion layer. Okay, this region is simply so large that this becomes a p-well region, and you will have, due to the electric field applied by VST, this horizontal electric field is going to move the charges, the positive charges, the PMOS, from the source to drain, and this current will become exceedingly large. Okay, even for a very small increase in VST. So that's another breakdown effect that could occur besides the avalanche breakdown. Okay, which might occur in the substrate. So the third breakdown mechanism is the near avalanche or snapback breakdown. This breakdown process is due to the second order effects with MOSFETs. You understand that the three terminal device consisting of source, substrate, and drain, the structure is equivalent to that of a BJT bipolar transistor. So as the device size shrinks, we may begin to see parasitic bipolar transistor action with with increases in the drain voltage. This parasitic action enhances the breakdown effect. Okay, so this is also a second order effect for a small channel device. If the channel length is large, you don't have this parasitic bipolar parasitic bipolar action. But as the device size is shrinking, but then increasing the drain voltage, since PN junction is reverse biased, your BJT action comes into play, and there's a breakdown of the transistor. Okay, due to the small size, because the source, substrate, and the drain are quite source and drain, they become quite close to each other. Okay, So the flow of charges, they won't require much large of energy barrier. All right. So this on the VSD is enough to or VDS is enough to cause significant electric field which might break down the device. Okay, by reverse biasing the PN junction. The fourth mechanism is that if the electric field in the oxide becomes large enough, so the breakdown can occur in the oxide, which can lead to a catastrophic failure. If silicon dioxide, the electric field at breakdown is of the order of 6 million volts per centimeter, all right, which to the first approximation is given by the gate voltage, the ratio of the gate voltage and the thickness of the oxide. You see the breakdown of the insulator is given in volts per meters, right, or volts per centimeters, which is given over here. So typical order of magnitude for silicon dioxide is 6 into 10 to the power 6 volts per centimeter. Now, as you go on increasing VGS, you go on increasing VGS, well, the electric field increases in the oxide, okay, and for small thickness oxide, TOX, or small thickness of oxide, well, the breakdown is given by VG, the gate voltage, or VGS, divided by TOX. Okay, so for small TOX and large VGS, the silicon oxide, which is otherwise an insulator, it might start conducting. Okay, so you recall that in the MOS and MOS structures, we had these oxides, okay, which are there to prevent the short circuiting of the gate directly with the semiconductor substrate. Okay, so this oxide over here and this oxide over here, they act like a MOS capacitor. They act as a dielectric. So you don't have the direct connection of the gate terminals with the substrate terminal. Okay, so this is the substrate or the bulk body substrate, and then you have this gate terminal over here. So if this oxide becomes conducting, then this gate is short circuited with the substrate. Okay, so we don't want that. So but if you go on increasing V1 or the gate voltage over here, okay, or this VDD, so much so that the oxide breakdown occurs, then the device results in a catastrophic failure due to the short circuiting of gate with the substrate. So that's the fourth mechanism. For example, okay, so there are some values over here. A gate voltage of approximately 30 volts will produce a breakdown in an oxide with a thickness of 500 angstroms. Now, however, a safety margin of a factor of 3 is common, which means the maximum safe gate voltage for the same thickness oxide, for 500 angstrom oxide, would be 10 volts. Okay, so 3 times less. This safety margin is necessary since there may be defects in the oxide. I mean, the oxide could be lossy. The oxide could be lossy. There is a factor associated with the oxide, called the loss tangent. So it's called the loss tangent delta. So if this factor is high for silicon dioxide, I mean, a very good oxide, silicon dioxide, would have the loss tangent of like 0.001. Okay, and if factor is high, it shows that the oxide is lossy. Okay, and the breakdown field could occur at much lower orders than what is known in the literature for silicon dioxide. Okay, so you need to keep a factor of 3 for safety margin. So so we must also keep in mind that the input impedance at the gate is very high, and a small amount of static charge accumulating on the gate can cause the breakdown voltage to be exceeded. All right, so in order to avoid that charge buildup at the gate, to prevent the accumulation of static charge on the gate capacitance of MOSFET, a gate protection device is used, such as a reverse bias diode. Okay, so if you are employing a reverse bias PN junction on the gate, you might, well, you can avoid the accumulation of these static charges. So it's usually included at the input of the MOSFET IC, just to avoid the static buildup of charges. So that's one way. And then you also have to keep this gate voltage approximately by a factor of 3 to avoid the breakdown of oxide and to avoid the short circuiting of gate with the semiconductor or the bulk body of the MOSFET device. Otherwise, you don't have any MOS capacitor. Okay, the plates are just like short circuit. Owing to the short circuit, there will be a huge gate current, and this gate current or this I square R dissipation loss might burn the device. Okay, so we don't need this catastrophic failure. So this IG is the gate current. So this could be very huge if the gate becomes short circuited with the bulk or the body. All right. So that's the breakdown effects that one needs to consider while designing a device. So the all the things, I mean, this happens in the actual MOSFETs, having dimensions, having the channel widths of typical order of in nanometers or sub microns, okay, point less than zero point 0.2 micrometers. You start having those effects because of parasitic bipolar action transistor that can take over. Okay, so your source and drain terminals, they can come closer to each other, so the charge carriers, holes or electrons, they don't need much of a barrier. Okay, I mean the VDS is good enough to lower the barrier. Okay, we have talked about this in earlier lectures. VDS can lower can induce the barrier lowering effect, and you can just in the device you can short circuit the drain and source. Okay, so as the size becomes smaller, this breakdown mechanisms like punch through, they become significant. So what happens is that the depletion region around the drain is completely extended. Okay, so it extends through the channel, it completely extends through the channel to the source terminal. All right, so that's again the short circuiting effect of the device. And this effect also causes the drain current to increase rapidly with only small increase in drain voltage. So you don't have any more IV characteristics. You're just shorting the device. So these punch through, um, there's a punch through effect. Then there is a drain to substrate junction breakdown. That's avalanche breakdown. So that's first. That's the second. Parasitic bipolar junction transistor behavior could be the third. And then you have this fourth. So there are four possible ways the device can break down. Okay.